tearing through the sky at a Mach fraction requires constant microsecond adjustments. A modern aircraft generates thousands of data points every second, just to keep the wings level and the engines burning. To actually read that information, altitude, heading, airspeed, a pilot traditionally has to drop their line of sight down into the cockpit and scan a dense panel of mechanical dials. At 500 miles per hour, physics makes that physical movement dangerous. Taking your eyes off the horizon for just one single second means the aircraft travels over 700 feet completely blind. Constantly shifting focus between the bright sky outside and the dark instruments inside forces the eyes to rapidly readjust. Over a long flight, this continuous scanning cycle accelerates cognitive fatigue and slows a pilot's reaction time to emergencies. Aeronautical engineers needed to solve this mechanical bottleneck. They had to figure out a way for pilots to absorb all critical flight metrics without ever breaking their visual lock on the physical environment outside the glass. The solution was the head-up display. This system was built specifically to eliminate those fractions of a second where a pilot is flying blind at near the speed of sound. To project data directly into the pilot's field of view, the aircraft first relies on a network of physical sensors mapped across its entire frame. This diagram maps out that hardware architecture. On the left, individual components like the inertial platform, air data computer, and radar altimeter continuously feed raw physics into a central HUD computer. But pure numerical data is difficult to parse during high-speed travel. The human brain cannot process complex raw telemetry fast enough during high-stress flight maneuvers. Moving to the right side of the schematic, that data flows out of the HUD computer and hits the symbol generator. This component acts as a translator, intercepting raw numbers and converting them into simplified visual language. This real-time translation functions as a filter. It aggregates millions of independent sensor readings into a unified visual set that a pilot can interpret during high-stress maneuvers. Delivering those translated symbols into the pilot's eyes requires specialized hardware tucked directly behind the dashboard, a compact, high-intensity projector. This unit takes the graphics rendered by the symbol generator and fires them upward toward the cockpit windshield. The graphics hit a piece of hardware called the combiner. As this cross-section shows, the combiner is a transparent glass plate angled perfectly within the pilot's natural forward line of sight. The surface of this glass features a specialized beam splitter coating. It catches the projected digital light and reflects it toward the pilot, while simultaneously allowing natural light from the outside environment to pass through. Looking through the combiner, you see this result. Crucial flight metrics appear to physically float in the empty air over the landscape. The system continuously adjusts its brightness, so graphics remain legible in direct sunlight or the dark. Instead of numerical readouts, the pilot interacts with intuitive shapes. Outlined in red here, the system maps out the aircraft reference symbol, the precise angle of the flight path, and a quick visual indicator of acceleration. This optical trick merges digital analytics with physical reality. It removes the need to look down, keeping the pilot locked on the target ahead. This design succeeded. Pilots experienced a drop in cockpit workload, able to maintain continuous visual contact with the runway, even during complex, high-speed approaches. But placing perfectly formatted data directly over reality revealed a quirk in human psychology. Human brains naturally gravitate toward bright, easily digestible information. In aviation psychology, this phenomenon is called attention capture, or simply tunneling. When tunneling occurs, a pilot becomes absorbed by the digital shapes tracking across the glass. Their eyes lock onto the overlay so intensely that they become functionally blind to physical events happening right on the other side of the windshield. To solve this cognitive trap, modern interface designers tightly curate the displays. Engineering efforts focus on identifying non-essential data and removing it to prevent display clutter. Engineers maintain strict limits on visual clutter. By keeping the total quantity of symbols low, they prevent the brain from treating the display as a solid object, ensuring the pilot's focus remains anchored in the outside world. Designing for extreme speeds requires an acknowledgement of human perceptual limits. Maximizing pilot safety depends on restricting the display to the minimum amount of information required for survival.